So I'll give it up for him.
Thanks. Yeah, my name is Barkas. I'm a software engineer at Spotify. All right, I'll start with a bit of an outline of how this is going to go. I'll start by introducing what Spotify is and a little background information about scalability. The next part will be a discussion of some ways of distributing computational work amongst a lot of servers and data. And the last part will be a bit about a tool we use at Spotify that helps us with this, and some interesting stuff we do with DNS, including using it as a configuration for distributed hash tables. All right, so what is Spotify? Some of you probably don't know what it is. It's an on-demand music streaming service. We have a native application that runs on your computer or mobile phones or some other devices. It's not web-based. And you can stream music from our servers. You're also to play your own music files and download the MP3s that you pay for. We have a premium service that you pay a monthly subscription fee for. With that you get support for mobile devices and offline playlists and some other sort of features. And there's also a free version that's supported by advertisements. Our playlist system allows you to make a playlist and have it attached to your account. And whenever you log in on any sort of Spotify device with that account, you'll have that playlist available. You can also share these playlists with your friends and even make them collaborative so everybody can add or remove tracks to them. And you can connect to Facebook and import all of your friends who use Spotify as well, and then you can send songs to each other and see each other's playlists in a nice way. And downloads that you buy or your own music, we now support syncing that to iPods, so you don't always have to use iTunes to do that if you don't want to. And we're available in 7 countries in Europe today. Our next big push is the US, and we want to be everywhere though, so eventually, hopefully, we'll be in your country, if you're not one of these already. Okay, so here is a rough overview of how Spotify works from a high level. I'll start at the bottom with all the different sort of clients here. As you can see, they're all connected to an access point, which is kind of a big proxy server that spreads the requests that they make and sends data back to them from all the different backend servers. You also see that there's some arrows connecting the clients to each other, and that's because we have a peer-to-peer protocol as well. So if you've already listened to some song and it's cached on your computer, that can be also sent to other Spotify users directly over this peer-to-peer network. And that saves us money on bandwidth costs. There's a web API here as well, but as you see, it only points to one of the backend services, and that's the browse service. You can do search and browse from this web API, but we want to add a lot more web APIs in the future. It's just this is what's available for now. And then here's a few of the backend services, a few of the most important ones. The playlist server keeps track of all the playlists and pushes the updates to clients when changes are made from a different client. The storage system has the actual music files themselves that you stream from. The user service handles authentication and authorization. Browse shows metadata for the tracks, albums, and artists. And also, it sits in front of the search service. So when you make a search query, the search service will give back a list of track IDs and artists and albums, and the browse service will then add the metadata to those results. So you get a nice list, including data, not just IDs. And the dots there indicate that there are a lot more services. These are just a few of them. It's drawing them all rather hard. Okay, so first, what is vertical scalability? The idea there is just to get bigger servers, more CPU, more memory, faster hard drive, whatever. An advantage to this is that if you have some software running on some server and it's getting too slow and you buy a bigger server, you probably are going to get a speed increase without having to do much to your code. You might have to make some changes, but they're usually kind of small. Another thing that's nice if you have very big servers is that they're easier to manage operationally. You don't having racks full of servers requires a lot of work from an operations team. You have to spend a lot of time just keeping that going. One of the negatives is that hardware prices, as you go to bigger and bigger machines, prices go up very, very, very high. And you have a limit on how big of servers you can buy. IBM and some are Oracle now sell some really, really huge machines, but still it's a few hundred cores or something, and that is not enough for everybody. Also, because we can't, we've hit sort of a limit in how fast we can make individual CPU cores. We need to have lots and lots of cores in machines in order to give them more speed. And to have one program take advantage of that, you need to use threads. And that can be tough, dealing with locking, trying to keep away deadlocks, trying to avoid race conditions in a multi-threaded program can be a big challenge. And if you have just one machine, it's a single point failure. Obviously, if it goes down, you lose everything. That's bad. So horizontal scalability is the other way to go. And I think really the only way to go past a certain point. You can always add more machines until you run out of money. You might not have to deal with threads at all if you go this way. If your program is single-threaded, you can run several copies of it, and that's what you have to do with Python. We'll talk about that a little later. So you might never have to deal with these sort of threading, concurrency, deadlock kind of problems. It's possible to run programs designed for horizontal scalability on Amazon EC2 or Rackspace. But you're pretty limited in the size of machines you can get from service providers like this, but they make it very easy to just spin up new machines all the time. First downside is you need some way of distributing the requests from your clients across all of these servers, because there's many of them. If you need to share data between servers, if they don't all have the data they need in order to perform their tasks, you have to deal with communication between services somehow. And especially if you need to do locking, that can be quite tricky. Having a lot of servers has a lot of complexity. You might still have single points of failure, even though you think you have redundancy, just because you have lots of copies of some service. And it might be harder to see that just because of all the complexity. And something I think is both a good and a bad thing is that designing for horizontal scalability means that you have to fundamentally think about that when you're starting building your application. It's pretty hard to go from a program that wasn't built for scalability at all and then try to make it work this way in the future. But also I think it's a good thing, because if you're forced to work this way, you will build your application from the beginning in a good way, and you won't have to rewrite it later. So why are we doing horizontal scalability? Well, we're big. We have over 13 million songs and over 10 million users, well over 10 million users, and they have a whole lot of playlists. They listen to a lot of music. They hear a lot of ads. It's a lot of traffic, and no one machine is going to be able to handle it. Also, we use Python a whole lot in our backend, and we kind of don't have a choice. The global interpreter lock, the GIL, means that you can't have multi-threaded Python programs that are able to use all the cores on your machine. So it's if you have just one program and you have an 8-core machine, you're wasting a lot of resources. But this is, I think, kind of a good thing. You're forcing to really build for horizontal scalability because you can't have all these threads. Dealing with the multiple cores, like I said, you have to have multiple Python processes. And this is basically the same thing you have to do when you need more servers than just one to handle your load. So going from a single machine to several machines is not as big of a step then. Also, when you're building from the beginning a program that you intend to run several copies of, you're encouraged to not share data whenever you can, because it makes it harder. And as you get big, if you're sharing data, those problems just get worse. If you need to synchronize across 50 instances of some service, then the locking is going to slow things down big time. All right, so now on to the next part about how do we actually design these sort of applications. What sort of things do we think about as Spotify? We have separate services for each feature. Whatever sort of network service you're trying to provide, you probably have a lot of different things that your backend has to do. And the Unix way to deal with a complex task is to have a lot of simple little tasks, little programs that do one thing well and put them all together. You can do the same thing with network services. Simple applications are easier to scale because they're simple. It's easier for somebody to understand them and deal with performance problems and things like that than having a more complicated piece of software. You can focus more of your time on the specific servers that need more focus. Which ones are being hit really hard, which ones have very high availability needs, like being able to have users log in, being able to have users play music, very important things. Other stuff is not as high a priority in a service like Spark. Development also becomes fast and scalable. You can add more developers. You have horizontal scalability of people if you have lots of little pieces that each people can work on separately. But this requires that you have well-defined interfaces between all these different services. You need stable, documented interfaces. And it's really the same thing as having modular design when building a large software system. All right, so you also need lots of different instances of the same service because a single one isn't going to be able to handle your load when you get to any kind of size. So if you have n instances of your service per machine, n is probably going to be some number equal or less than the number of cores that machine has, because each application should be able to fully make use of the CPU core. And then you also have many machines. So you need a way to spread your load across all of these. And there's a few ways to do that. One of them is hardware load balancers. These can be really expensive or less expensive, have some really fancy features that do a lot of nice things automatically for you. Round-robin DNS is a really common thing to do, where you just have a bunch of identical DNS records that point to different hosts. And the clients then trying to talk to those hosts will grab one at random. And there's proxy servers, especially for HTTP-based stuff. There's tons of proxy servers to use. Varnish, Nginx, Squid, Lighty, Apache, those are just a few of them. A nice thing with proxy servers also is that you sometimes get caching for free. All right, so you also have to share data, probably, at some point. Excuse me. If you have more data than a single server can handle, it could be too big to fit on disk, or it could be something that you need such performance for that you need to keep it in memory, and you're really limiting how much data a single machine can have. So split up your data set so that each instance or server is responsible for some subset of all that data. If you share nothing, really, in your service, this is pretty easy to do. The only challenge is that you have to direct the requests to the correct instance for that data. But if you want things like replication, which you probably do, because failures do happen, then it gets to be a much harder problem. So this guy named Brewer came up with this theorem called the CAP theorem. And CAP stands for consistency, availability, and partition tolerance. In this context, consistency means something like, if you write some data and you want to read it back, you should get the same thing. Availability means that, for example, if a node goes down and you want to still be able to use your whole distributed system, you can't break the whole thing, and you also don't want to degrade performance too badly. Partition tolerance means that if the systems in the whole distributed system become disconnected somehow, if you have your fiber between two data centers go down, then you want those two data centers to continue to be able to operate independently. And in the middle is the cake. If we could have all of these things, it would be awesome. But the whole thing with this theorem is that that is impossible. You only get to have one or two. The cake is a lie. So eventual consistency is something that a lot of people do. They relax their consistency requirements because a lot of services don't need to have really strong consistency all the time. For example, the Spotify playlist system is this way. It would actually be impossible for us to have it be consistent all the time because we want users to be able to go offline and make changes to their playlists. Then when they come back online, It should be merged with the canonical playlist that we have on our servers, and all of their friends, if it's a shared place, will see those updates. It's nice to have this consistency happen as soon as possible, but we can make it all happen in the background if there aren't any conflicts. So we have to design a system like that to handle conflict resolution and just never have conflicts. S3, Amazon's S3 is an eventually consistent key value store. A lot of NoSQL data stores work in this sort of eventually consistent way. If you read right after you write some data, you might not get back the same thing. An example of a data store we use at Spotify, we started using pretty recently, so it's not in very wide use, is Cassandra. Cassandra is built on a combination of ideas from Amazon's Dynamo key value store and Google's Bigtable, which is a column-oriented database. Cassandra has the AEP of CAP. It is very available, and it is tolerant to partitions. Writes to Cassandra are very fast, reads are pretty fast, but writes are faster. And it handles replication in a very complicated but intelligent way. And it's partition tolerant in that if you have a node disconnected from the Cassandra cluster, when it comes back, it will try to update all of the replication stuff that may have happened on it and the rest of the cluster. It'll update based on the changes that happened on it on the rest of the cluster while they were separated. But a nice bonus with Cassandra is that you can get some consistency if you really want to. You just have to sacrifice availability or partition tolerance. An example of that is, of how you do that is when you have a specific request to Cassandra, you can say that you want to write with each level of write strength, and that means you will write to every single replica that's configured for that Cassandra cluster before returning success and saying that the write worked. This obviously hurts availability and partition tolerance, because if one node is down or disconnected, that write is going to fail. A little bit nicer thing to do maybe is a quorum write, and this means that you have a quorum of the replicas are written to before you say it's successful. A quorum is just a simple majority of them. But in that case, if you want to read back, you have to do a quorum read as well in order to ensure that you get the most up-to-date data. And that means that you will ask all of the replicas for their data, and once you have a majority of them agree it has the newest version of that data, then you have a successful read. Cassandra is a pretty new project, so it's somewhat immature. Things are changing, but it's pretty solid at this point. There's a pretty steep learning curve for it, though. You're going to have to spend a lot of time learning how to configure it, learning how to use it, or you're going to be bitten by nasty surprises. And nasty surprises when it comes to data are really bad. I would recommend that if you want to use Cassandra, you should have at least 1 or 2 people in your organization spend a lot of time really looking into it, reading documentation, subscribing to mailing lists, maybe reading source code. It's Java, it's not that scary. Sometimes, though, you really, really need consistency. And for example, if you want to do some kind of locking, you want to do atomic operations, you need consistency. Some examples of this that we have at Spotify is if you want to create some globally unique key, like a username. Usernames in Spotify are unique. If we had 2 people with the same username, we would have all kinds of problems. Or transactions in billing. If you have a lot of different processes that do your recurring credit card payments, and they check some data store to see when the last payment happened, and then go ahead and charge the card they have on record. They need to lock that flag or timestamp or whatever is used to say when that last payment has happened while they do the actual credit card processing, and then come back and release the lock updating that value to avoid having some other process come along and say, oh, I'm going to try to redo this subscription as well, and then the user gets double charged, and then they call you and they scream at you. Postgres and other relational databases are really good at this sort of thing, and we use them for this sort of thing. You can get pretty high availability by replicating, having lots of read slaves, and then only having to write on the master. And you can deal with the possible failure of the master server by having a hot standby master. And that just, it's another slave that doesn't get any sort of traffic And if your master goes down, then somebody comes along and flips a switch and makes the standby be the new master. But you should really only store what you absolutely have to in these sort of global databases, because they are going to be global if you really want to limit their size so that you can handle growth. And I just want to say that Postgres isn't good for only this sort of thing. You can use Postgres for all kinds of stuff. You can use MySQL for all kinds of stuff. You can shard your data and use them in the same sort of ways I was talking about using a key value store, for instance. But at Spotify, we are trying to move more towards using the standard for a number of reasons. It's kind of cool to work with. Okay, so here's some miscellaneous tips for dealing with having a lot of instances of the same service. Processor affinity. In Linux, there's a command where you can tell the kernel that a particular process ID should be sort of pinged to a certain CPU core. And this is really nice for being able to get good cache hits. If your process, the scheduler is moving your process to different cores, then it's not going to be able to make the best use of the L1 cache, because that's per core. You really got to watch out for connection limits when you have tons and tons of instances of service. If you have 20 different servers running each 10 instances of some service, then that's at least 200 connections. More if you're using connection pooling, which you probably should be, going to your PostgreSQL or whatever database, and they usually have limits by default that are a bit low. One easy kind of data to share is cache data. If your different server instances create some kind of data that they can reuse, they can shove that into memcached, and everybody can share memcached or a selection of memcached servers, so that they don't each have to keep their own cache of the same data copied on all the different machines. And the operating system's page cache is a really useful thing, especially for data that you're just doing a lot of reads from. If you have several instances of some process running on some machine, and they're just reading from a Berkeley DB or Tokyo Cabinet or whatever sort of database, then having as much of that disk file be in the page cache as possible means that they all get to share this sort of faster memory access than having to hit the disk all the time. Some Spotify services, like our browse metadata service, it's absolutely critical to have the page cache. And there's some utilities, there's a syscall called POSIX FFIs, where you can even tell the system that this file should be in the page cache, or this one should not, because I'm only ever going to look at it once. Or if you can do like we do, and you just take the index file, cat it with the output to dev null, and then start up your service, the page cache is warmed up. All right, so now the last section is going to be about some tools and methods we use in Spotify. Supervision is a little piece of software that was developed at Spotify. There's another piece of software called Supervision, which does similar stuff by Dan Bernstein, but it's not the same as ours. Supervision is a daemon that launches other daemons. We usually configure it so that it will automatically launch as many instances as the server has cores, -1. We usually reserve 1 core for other sort of operating system stuff, or cron jobs, whatever. So all the CPUs are pinned, other stuff can go on the server still. If one instance of the service fails to supervise, we'll restart it automatically. And if you upgrade the software, by default, supervise will restart all of the instances eventually. You can configure to not do that if you want to do it yourself for whatever reason, but it's nice to have it happen automatically so you don't have to manually restart 15 different things for a 16-core server. There's also a different open source software that does a lot of what supervise does. It might do everything supervision does. I'm not so familiar with it, but you might want to take a look at it. It's called systemd. All right, so how do we deal with binding services and balancing load between them? Every service in Spotify has a DNS record and SRV record. There will be copies of this record for every single instance, every single host and port combination of something that should be queried for that particular service. Clients, which is usually the access point, but sometimes other backend services talk to each other, will find these instances using this by resolving this DNS record. And there's weights and priorities. I'll show you an example SRV record in a moment here. And as you have several different ones, you can set priorities of which one, like you should pick this one because it has a low priority, or if several different records have the same priority, there's a weight so that you can affect the random distribution of which one to pick. But clients sort of have to do everything. DNS just has this information. It doesn't do the load balancing. So you have to set up your application to pay attention to what these priorities and weights and all that mean, and automatically grab the right one, right random one. But you can do it in the library, so you don't have to implement it in every single thing. And yeah, also retrying in case of failure. If instances go down as they do, then the client application has to be able to cope with that, has to know about retrying, backing off so it doesn't retry every millisecond or something like that. Okay, so here's an example SRV record for a service called Frognicator. It frogs some bits. It's HTTP based, so that's what the little HTTP means there. And example.com is the domain of our example. Like all DNS records, it has a TTL of an hour here for this example. It's an SRV record. The priority is given first, and then the weight. I hope I didn't hit these backwards. It's very confusing. And the next field is the port number that the service listens on, and then the host name of the server. We also sometimes use Varnish or Nginx, not depending on more than just doing round-robin DNS. SRV records give us weighting and stuff, but sometimes it's nice to not have tons and tons of DNS records. So you only need to have one SRV record per server pointing at the Varnish or Nginx instance. And like I said before, they can add caching. Sometimes that's really useful for static data like browse. We use, especially for our web API, we use Varnish or Nginx. I'm not sure which one. We use both. Okay. So that people using our API, if they make the same request over and over again, you really want caching, obviously. Okay, so on to distributed hash tables. Probably many of you are familiar with these, but not sure. In this drawing, I'm showing like a ring that represents the key space for a hash table. And the little circles on that are nodes using the distributed hash table. And those nodes are each an instance of some service that is using this DHT to distribute their load. And each node is responsible for the range of keys. The keys come from using a hash function on the resource name. It could be like the track ID for browse, or it could be the username for the user service, or playlist ID, and so on and so forth. So each instance is responsible for the range of keys behind it, between it and the previous node. So here B is responsible for everything in the range of 14 to 3F. So a key of, I can see that, 1C fits into that range, and the same goes on the other side of the ring. And if you want redundancy, if you want replication in this way, the way we handle that is that you just hash that key value again. And you have to sometimes do that several times to make sure that it ends up on a different instance. And then the client application itself has to then make sure it writes to each instance that should have a replica, or to check them all for the data that they're reading and one's down. A kind of tricky problem happens when you add or remove nodes. This ring will obviously change then, and the range of hash values that a node is responsible for is different. So then you have to transition data, and we have some ways of handling that, but it's a bit tricky, and it's not something I'm super familiar with, so I don't really want to go into the details about that, but it is something you have to keep in mind. But even if all of your service instances have access to the same data, if they don't need to just have some subset like this distributed hash table is really useful because of cache locality. The similar requests, the smaller range of requests will always go to a single node instead of being randomly distributed with the weighting of the SRV records, so that more stuff will fit in their cache that they're asked for regularly. And here's an example of some of the DNS records we use for these DHTs. The first one is the token record. We have one of these for every instance of a given service. It starts with the string tokens, the port name, the port number, excuse me, and the host name. And that's the TTL again, and it's a text record, so you can have freeform text as the next field. And that is the last key that that particular service instance is responsible for. Because the key space is a ring, it's modular arithmetic going on here, then you only have to keep track of the end of the ring, because you know about all the other nodes, so you know where they are, so you know where your range starts. And we also have these other special records for configuration of the entire DHT, and you have one of these records for each service that's using distributed hash tables. And the first example is for Obfuscator again. It starts with config, saying that this is a config type text record, and then the name, the SRV record name, TTL text record, and configuration options. For this one, we have just one. It's slaves equals 0. That means the client doesn't have to deal with writing to replicas. It doesn't have to look up from replicas. You might use this sort of setup like in the last example in the last slide of when everybody has all of the data. So then your client can say, okay, well, I know I should use DHT. Oh, but that node's down. Well, I can actually get this from everywhere, because slaves equals 0 means that it's not replicated, which should mean that everybody has the data, because you should always replicate it somehow. Sorry, that might have been a little confusing. The next one is a bit more obvious, I think. It's all the same except different configuration options. And this one says there's 2 slaves, so that means we have 3 replicas in total. And redundancy host means that not only should the clients repeatedly hash the key until they find another instance, they should make sure that instance is on a different physical server, which they know because they have the host name in the tokens records. Okay, so if you're interested in DHTs, which who wouldn't be? They're awesome. You should take a look at, there's a couple of papers that I think are pretty good. Cord is a distributed hash table, a way of handling that. Pretty neat stuff. And then there's Amazon's Dynamo key value store, which is inspired by Cord, plus a lot of cool stuff that Amazon did. These links take you to ACM pages where you probably have to buy the PDF, but if you Google the name of the paper, you'll find it somewhere else where you don't have to pay. Because their authors make them available elsewhere. It's nice. All right, and one more thing you should remember. Dev null is web scale. It does writes really, really fast. I mean, it's not the most consistent thing, but yeah, if you haven't seen the video I'm referencing here, you should get the slides from the website and click on that. It's quite funny. All right. So does anybody have questions, or you can send them to me later with my contact details here.
Okay. Any questions?
Do you use only Python or other languages for your Spotify?
We use many things. We use mostly Python in the backend, but we also use Java, a little bit of Scala, and C and C++ to some degree. And for the client applications, they're mostly C and C++, but also like the specific stuff for what the platform requires. Like there's a WebOS Palm client, and that uses a lot of JavaScript because that's how WebOS works.
What was the second and the question?
I just want to ask about DHTs. Have you implemented those from scratch, or are you using something? And I'm not sure I understood how the DNS worked, how the nodes were just doing DNS lookups to get integration. Is that?
Yeah, I think that's something we did ourselves. That's somebody at Spotify, maybe a group of people. Yeah, a couple of people probably worked together and came up with that idea. Hey, I want to talk about it because I came to Spotify only a year and a half ago, so a lot of the stuff was in place, and I thought it was really kind of a neat way to do things. As far as I know, nobody else is doing exactly the same thing.
You can sort of dive into more of that, and yeah, it's neat, it works, it helps out a lot. but it's also maybe not the best way to do it. And that's partly why we've been moving and looking into Cassandra, because it solves those problems for us where we had to do it ourselves. That makes it much easier API. The client library is just the normal Cassandra bindings, and then, okay, you have to trust Cassandra to make the correct choice, but it's more advanced than our solution, in a good way.
I have a question. So there's been a lot of talk about Cassandra lately, especially about 3-4 months ago when it was the hot thing to do. Before Facebook moved to HBase, and people said that Twitter was moving into others to HBase, and people were getting Cassandra. Are you having performance issues, cases where, like, during compaction, the Java daemon or doing garbage collection, the Java service goes down because it doesn't get enough I/O, for example, EC2?
We're not having those problems yet, but we're very aware that they could come up. We're not running on EC2, we're running on our own hardware for Cassandra at this point anyway. So we have a bit more resources than you get in EC2. But so far, with what we have in Cassandra, we've had small enough amounts of traffic that it hasn't been a problem. But we're obviously going to ramp that up. We're trying to take a slow transition to make sure that compaction problems and other sorts of performance problems don't kill us.
Yeah, so we actually have a lot more traffic than Nick is telling you here, but we don't use it live. So, as mentioned, we migrated the playlist system to Cassandra, but right now only a small percentage of the playlists are actually served from it, but we put a dark load on it, so we send the request from all the playlists to Cassandra as well, even though that doesn't matter, and then we can see these sort of issues and handle them accordingly. But so far it's been working okay, but you have to know about it.
So you talked a little bit about load balancing. I was a little confused on how you actually do load balancing. I don't know if that was part of the DNS hashing. But you didn't mention HA proxy, which is also very, very nice, and it's a great alternative to anything else in the list.
Okay. Well, I've never used HA proxy. I have heard of it before. But
So I guess then my question was like, are you just using Varnish and Nginx to proxy, or is it all round robin, or what are you doing to actually load balance between services?
we're doing round robin quite a lot, and often Varnish and Nginx. I think that's, no, we do have hardware load balancers. If not already, they're coming soon. But yeah, it's a big mix of stuff. The DNS stuff is, load balancing has to be done at the client level, and we have libraries you just like import to do that and do the automatic backup stuff, back off stuff for your requests for you.
Does that your clients support?
Yeah.
So I have one more question. So you're doing round robin with DNS. So the first part is, how do you handle cases where part of you have 3 different nodes and one of them goes away and you have to update the DNS? And the second one is, are you running just in one data center or are you running multiple data centers?
Okay, so for the first question, we manually update DNS. If a node goes down, and it's going to be down for a while, we have to have somebody take it out of DNS and reload the name servers. That doesn't happen all that much, I guess. And if it's just a temporary failure, it's no big deal because the comments are written to try other instances. And as for data center recapture, there's two in Europe and one in the US.
What's your average TTL on the DNS servers?
I think it's probably 60 seconds, but it varies.
Any other question?
With such a low TTL of 60 seconds, do you have issues with the servers that have the lowest IPs numerically getting more traffic?
Not that I know of. Based on graphs I've looked at, we have a lot of graphs of how much traffic we get. It seems to be distributed how we want it to be. The DNS stuff is really more owned by operations people. people. I mean, I know about it. We write in the zone files, and they didn't deal with handling the servers more. So unfortunately, I don't know everything about that. But yeah, there hasn't been any problems with uneven distribution as far as I know.
Any question? I have another one. So with the horizontal scalability, one of the problems is how do I track logs for all those instances, their statistics and such. In Amazon, you have CloudWatch. Right now, they release the custom metrics for everybody. What do you know that Google has a specific special infrastructure for dealing with real-time analytics data from all their servers? What does Spotify use, Ganglia or?
For logs, we don't have real-time log monitoring. We do collect all the logs. They all go to one central place and get shoved into HDFS or HBase, and we have Hadoop jobs that are run at least daily, quite often on that data if we need to get some analytics out. For more real-time monitoring, it's not using the logs. We use Newman for statistics, just making graphs, and we use Zabbix a bit for being notified of failures.
Any other question?
So LinkedIn released a bunch of really cool open source libraries. Have you guys taken a look at those?
I have not, but I will.
Any question?